Hello. So 1.3, the section originally started off with algebraic expressions and how to simplify them and how to evaluate them. But now we're going to take real life problems, some pretty lame ones, and we're going to set them up as algebraic expressions, and eventually we're going to work our way to algebraic equations. So we have a process when we have a real life problem that we want to go through, and I know it seems really daunting, but you have to remember that most kids skip word problems because they don't like them or they think they're difficult. But if you kind of have a process in mind, it's not too bad. And this goes kind of quick. So we're going to be writing a verbal model, which just for me involves some words, abbreviations that kind of sets up the math for you. And then this diagram says to assign labels and then write the algebraic model, solve the model, yada yada. So for me, when I set up the verbal model and then I set up the algebraic model right underneath it, that's kind of my way of defining the variables. I'm lazy, so um, of course we're going to solve it if possible. That's the whole end goal of when we set up these problems. So here in Algebra 2, we're going to do a lot of story problems. So you own a lawn care business and you want to know how much money you can spend on gasoline to drive to out-of-town clients. In a typical week, you drive 600 miles, 40 gallons of gas. Oh boy, this must have been written a long time ago. Gas costs $1.25 a gallon. And your truck's fuel efficiency is 21 miles per gallon on the highway and 13 miles per gallon in town. So that was a lot of information, and I don't know if we need all that information. So I just want to know how much money I spend on gasoline. And if I think about, me driving my own car, obviously I know how much I'm going to spend on gasoline when I spend it. But if I know how many gallons I'm going to need, and I know how much a gallon of gas costs, I think that's all I need. So for my verbal model, it's really not too complicated here. We're just going to write down the total amount of money that we're going to spend, like the end of my algebraic setup, what I want to figure out. And if we knew the number of gallons and we multiplied that by the price per gallon, I think that'd be enough information. So that is what I'm going to look at as my verbal model. So now I'm supposed to set up variables to represent all these things. So total T sounds good. Number of gallons, let's say N, and then times price per gallon. How about P? Now I go back and look at the information they gave me. So we use 40 gallons of gas. That is the number of gallons. And then the price per gallon is $1.25. I wish. And the total is actually what I want to find. So I'm going to leave that as a variable. And then I grab my calculator and I type 40 times $1.25 and I get $50. So this is a really basic example and probably nothing this easy would show up on your exams for my class. But the idea is, can you take what you see as a logical solution to something, write it in an algebraic way? That way you could set it up so a machine could understand it. That's the whole point of doing these, right? We're going to program machines and computers to do these really, really fast so humans don't have to do all these little things all the time. The other thing that we could do is we could write a whole sentence about I'm going to spend $50 of gasoline going to my customers. That's that's the other tricky part of math. It's fine to be able to do the math, but if you start shouting out mathematical answers at people, if they've hired you to solve things, they don't want to hear that. They want to hear actual words. So you have to think about how you're going to talk to your customers if they want you to do the math for them. So this next problem, the table gives the height to the top of the first few stories of the building. So in the lobby, which we're going to call story 0, is 20 feet tall. And then if you go up to the first floor, the top of the ceiling there is 32 feet and yada, yada, yada. So this question says determine the height of to the top of the 15th story. Now, I sense a pattern going on here. After the lobby, this looks like it's going up by 12 and then going up by another 12 and going up by another 12. So we could kind of continue the pattern out all the way to the 15th story. I don't know if that's a real efficient way to do it though. So if I think about a verbal model here, let's start with my total height is going to be, we're going to start at the lobby, right? Because the lobby is the weird one. But then it's going to go up the change for each story. But then you got to figure out how many stories you actually went up. So by the number of stories. I know you're like itching to just throw numbers into this. That's coming soon, don't worry. So total height of H. Lobby plus total change for each story. Making up whatever variables I want. That's the kind of cool thing about math. You can really do whatever you want. And then the number of stories. Good. So let's plug in what we know. The lobby height was 20. The change for each story we decided was 12, 12, 12. And then the number of stories that we're going to be going out here is the 15th story, right? So we're going to be evaluating this expression at 15 stories up. So on our calculator, 20 plus 12 times 15. 200. Okay. And I know the writing of the verbal model seems like it slowed us down, but what it really does is it kind of maps out the problem for you. Again, we're doing some real basic examples. They're not going to be this basic all the time. But think about in English class when your teacher assigns you to write an essay, or even in one of your social studies classes, and you have to kind of map out your ideas first. And that's what we're doing when we write a verbal model. It doesn't take me long at all. It takes me like, I don't know, 4 seconds. And then I'm done. I'm ready to go. Next question is interesting. It's about 2 airliners. And the Boeing seats 100 more passengers than the McDonnell Douglas. And the 2 models together seat 696 passengers. So we're going to set up a model and then we're going to solve it. Okie dokie. So, if I look at all my information here and I try to kind of map it out, the Boeing, I'm going to set up kind of a system of equations here. The Boeing, I'm going to skip the verbal model if you don't mind on this one, 100 more passengers than McDonnell Douglas. So 100 more than the McDonnell Douglas, any variable you want. And then the 2 together would seat 696 passengers. So if I took the Boeing and I added to that the McDonnell Douglas, total to 696 passengers. Now, there's a couple of ways you could approach this. What some people do is they look at the difference between the passengers and they kind of figure it out from there. But what an algebra teacher would see is this is a really nice system of equations that says the Boeing represents 100 plus McDonnell Douglas. So these are interchangeable things. So instead of Boeing right here, let's call this 100 plus another McDonnell Douglas, right? So if I look at this equation now, 2 McDonnell Douglases plus 100 equals 696. So if I solve this, then I divide by 2. 96 by 298. So McDonnell Douglas equals 298. And the Boeing, remember, was 100 more than that, so 398. There you go. Not a real great, like, real person answer. If I was actually trying to give that information to people, I would probably label it a little better and obviously write a little nicer. Okay. A rental car comes. So when you rent a car, they charge you kind of a flat fee. This particular one is pretty cheap, $4 per ride, I guess. Maybe more like a taxi, and it charges 23 cents per mile. First, we're going to write an equation that represents the relation of the miles and the cost in dollars. So the total charge, oops, and it doesn't really say anything about number of rides, so let's just assume we like get in the car and then we don't get back in later. So we're going to call it the initial fee. But then adding to that the cost per mile. But you got to multiply that by the number of miles. So I'm going to skip the variable part because I know a few things. In particular, I know that the initial fee is $4. And then I know that the cost per mile is 23 cents. So we're going to write as 0.23. And then this Oh, one thing I just need to point out is they told you what variables to use for number of miles and then the total cost. That's why I chose C there. Number of miles, I don't know, and they said to use M for miles. So there you go. And all I want is the algebraic equation that'll represent this situation, and that's what I have. So you want to buy a paperback or a hardcover book for 5 cents, and you're going to buy them one or the other. Paperback costs $6.95 and a hardcover book costs $24.99. Write an expression for the total amount that you must spend. Now, this wouldn't be too difficult if I allowed you to use more than one variable, but I'm only going to let you use one variable, so I'm going to make it a little tricky. So we're going to start with total cost would be the cost of a paperback times the number of paperbacks plus cost of a hardcover times the number of hardcovers. But this is a little more complicated than that because I'm only going to let you use one variable within this body of the equation. So the total cost, let's say, is C. Cost of a paperback was $6.95. And then let's use, it doesn't tell me what variables, so let's use X to represent how many friends get a paperback book. Plus, hardcover book is $24.99. And this is where, if I was nice, I just let you use another variable to represent how many hardcover books, people got hardcover books. But instead, if I know I only have 5 people to buy for, if I bought 4 of them paperback books, that leaves 1 for a hardcover book. If it was 2, it would leave 3. If it was 3, it'd leave 2. So the way I'm getting those numbers so quickly is because I'm taking away from the total of 5 people. So what if we called this 5 minus X? That's one way that you can kind of get around using more than one variable. So now using this expression, 3 friends got paperback books. $6.95 times 3 plus $24.99. And then 5 minus 3, also known as 2. So a little calculator action. Like $70.83. All right. So this next one, they took data from 1980 to 1990 of the average weekly earnings modeled by this. So we'll learn about more of this later on in the semester, but they can take data and create a model, and then we can use that model to extrapolate data into the future. So T is the number of years since 1980. So within these models, the data is only for those 10 years. So you're kind of assuming like the trend continues, and then you're also pretending that time kind of started in 1980. So approximate the average weekly earnings in 1980 and then in 1990. So remember what they said about T. T is the number of years since 1980. So in 1980, there have been 0 years since 1980. So T is 0. So we're going to go ahead and evaluate the expression at 0. And that'll give you 270. And then in 1990, that has been 10 years since 1980. So we're going to evaluate the expression at 10. I should be able to add that, guys, but not today. 145, 415. All right. There we go. And then a phone company charges $13.99 per month. And then you are, back in the day when we had actual phones in our house, you had to get charged for long distance and long distance phone calls during the week versus the weekend. There's different prices sometimes on certain plans. So 10 cents per minute during the week and 8 cents per minute on the weekend. So write an expression that gives the total monthly bill, and then we'll figure out what's going on with the data afterwards. So I'm going to kind of skip the verbal model step for now. But the total monthly bill, the total, equals this $13.99 is just costing you like one payment per month. So you just pay the $13.99 because it is just for a monthly bill here. plus 10 cents for a long distance call during the week. So I'm going to say K. Oh, sound good. And then 8 cents for all the calls made on the weekend. So now evaluate this expression. There's no way for me to use more, just one variable in that one. With 30 minutes in the week. So 30 goes in for the K, where it would have been nice if I would have paid closer attention to what I assigned. And then 50 minutes on the weekend. Oh. $20.99. Well, my phone bill is not $20.99. Must be talking to old school phones. All right, one more. So the gift shop advertises that they will engrave any gift purchased at the store for 6 cents per letter but the first 3 letters are going to be free. So a desk plate sells for $22. We're going to write an expression that represents the total cost of buying the plate, but we're going to have it engraved. So we're going to not read this part of the question yet. We don't know anything about this 15, so hold off on that. So the total cost is going to be the desk plate, which is $22, plus 6 cents. And then it wouldn't make sense just to put a variable after the 6 cents because you're not going to be paying for all of the letters that you're going to engrave. You're only going to be paying for the ones that are after the free letters. Like for instance, if you did 10 letters, you wouldn't be paying for the first 3. You'd only be paying for the 7. If you did 12, you'd be paying for 9. So the way we're getting that is we're taking how many letters that you're engraving, but we're subtracting the 3 free ones. That's going to be our expression. So $22 plus 6 cents. If I engrave 15 letters, that's great, but I'm only paying for the 12 letters there. $22.77. That's my little Logan man that you're hearing in the background if you heard him. All right, and that's the end. Good timing because Logan's hungry.